Okay, so today's lecture will be on the concepts of stresses and strain that is applicable to biomechanics problem. So we'll quickly revisit the basic concepts in this lecture. So the first slide that comes into mind is regarding deformation of a solid. Okay, so the solids can deform when they are subject to forces. They are either compressed, maybe stretched, so they are under tension. They can undergo bending and they can undergo torsion. So compression, tension, bending, and torsion are different modes by which a solid can deform. They can maintain or lose their shape depending on the type of solid, but if this deformation can be small in rigid material and can be more prominent in more deformable materials. As you all know that we have the Hooke's law. So the Hooke's law, the ratio of the force to the displacement is constant. So we have the Hooke's law defining, based on which we can actually write the very important equation that F is equal to K delta or delta X, as you can see. So the restoring force is basically equal to, you all know that F is the restoring force, and F is equal to the stiffness of the material and the deformation delta, or this is delta X in this case. So this is a 1D problem, a linear deformation of delta X. All materials existing on the earth basically has stiffness. So stiffness of a material is the property by which it resists deformation. Okay, so anything, so we are dealing with bones, muscles, ligaments, soft tissue, hard tissue, whatever, they undergo deformation of different types. But if we actually consider the simplest form of deformation, we can explain it or relate it to the stiffness of the material. And the stiffness of the material, keep it in mind, very important, depends on its material property as well as its geometry, both. So together with the material property and the geometry, we can define stiffness of a material. Now, what is stresses? So the stresses are sort of the resistive forces per unit area, as you all know. So if you apply forces on a body by virtue of the property stiffness, there it can resist this deformation, and reactive forces, as you can see in the picture. I'll just highlight pointer options, highlighter, oops, oh, it's highlighted. Where is the laser pointer? Yeah. So you can see the resistive forces per unit area being generated within the body, which actually resists deformation. So you all know that we had studied in engineering mechanics two courses which actually together form the subject engineering mechanics. One is the rigid body mechanics, the other is the mechanics of deformable bodies. So if we consider deformation within the body due to forces, the concepts of stresses and strain, which is stresses are generated within the body. So unless a material is undergoing any sort of strain or deformation, stresses do not actually occur or are never generated within the body. So it is generated, the stresses are generated, and the normal stress is sigma is the ratio of the force to the cross-sectional area of the body. Strains are related to deformation, and the deformation is related to the size of the object. So in a very elementary manner, we can define that it is deformation per unit length. If it is a case of small, a rod, so it's where it is acted upon by forces P, external forces P, and if there is a deformation delta, so delta by L or delta L by L, whatever way you can call it, it is basically called the uniaxial strain. So, but it is unitless and measures only the fractional change in the body due to the external forces. Young's modulus is a material property, so you are quite aware of the effect of changes in Young's modulus. So if we do a material characterization of, say, a ductile material and a brittle material, so you know from the stress strain curve that how the stress strain curve will vary in case of a ductile material and in case of a brittle material. And the linear portion of the graph, you can, from that stress strain curve, linear portion, you can actually figure out the Young's modulus. Okay, so from stress versus strain, the linear portion, small, you can easily find out the Young's modulus of the graph. The slope of the stress versus strain is the modulus that depends on the type of material. So a material is characterized by Young's modulus, and of course Young's modulus, basically the stress, according to the Hooke's law, the stress is proportional to strain and the proportionality constant is the Young's modulus. And mathematically you can define it like this. So F by A is stress and delta X by L is strain. So Young's modulus is, if you relate it to the resistive forces, the length of the body, the area of cross-section, and the deformation delta, then you can actually relate delta with also Young's modulus, which is FL by AE. Okay? And if you define stiffness from this, try to define stiffness. Oops, sorry. If you try to define stiffness, you can see very easily how you can define it here. So if the force divided by the displacement, resistive force divided per unit displacement would come out to be AE by AY by L. Okay? So it is the Young's modulus, it is the length of the specimen and the cross-sectional area that contributes towards the stiffness of the material. Stiffness can be defined also as the resistive force per unit length, per unit deformation. That way also. So people who have studied finite element analysis, they are quite aware of the term AE by L as the stiffness of a bar or a link. So you'll come across many inelastic material in the course. Of course, its behavior, it's the material behavior the linear behavior of the material only lasts up to a certain strength, so a certain stress level, that is the yield strength. The material can continue to deform, but they won't restore their shape. So this is from where the inelastic behavior starts. In highly ductile material, this is also visible. So beyond the yield point, the material exhibits inelastic property or plastic deformation. So they actually undergo deformation and they don't retain their shapes. Okay, so that means the material undergoes distortion. So for very high strains in a material, so this material can break. Then the shear forces, you know what is shear force, shear strain, and shear stresses. So if you consider a body of this shape, and this body is acted upon by a force on the top, maybe you can put a force on that on the opposite side as well, but you can fix it. The lower the bottom layer can be fixed with applying a force on the top. I mean, gives you the same result. This, you can see the shear forces actually is trying to change the shape of the body. Okay, it is trying to distort the shape of the body. So shear forces actually produces distortion. Okay, and this distortion can be measured from the shearing strain, which is defined as the angular deformation. Right? So the shearing strain here is expressed in the angular fashion. So we have, although as it is very small, the shearing strains are small in nature. So we can express it as ratio of two dimensions. That is, one is the deformation along the force, shear force, that is delta x, and the original length, which is L. Okay? And the shear stresses, as usual, is the force on which is acting on the area. So it is basically acting, it is the shear forces are in plane here. In plane means that the plane on which it is acting is oriented along the direction of the applied forces. Okay, so F divided by the area on which it acts is the shear stress, and shear strain has been defined already as the angular deformation. So here we can define the shear modulus like we have defined Young's modulus or elastic modulus. Shear modulus can also be defined as the ratio of the shearing stress versus the shearing strain. The shear modulus S also relates to the Hooke's law, and this is defined in mathematical fashion as narrated in the slide. Now, volume stresses and strain is connected with deformation of the solid when it is submerged or it is pressurized from all sides. Consider the case of a submerged body within a fluid. Typical example is a submarine acted upon by the fluid pressure all around. Okay, so the pressure from all sides can actually lead to change in volume of the solid. So that is a situation where we actually are looking into the effect of volume stresses. So there is a volume strain and a volume stress which can be calculated accordingly. So here also the volume stress is F by A, the total, if you consider a small area of the material being subjected to the fluid pressure, so the force by that area would give you the volume stress, and volume strain is measured as delta V, change in volume, by the original volume, because the whole volume is being subjected to external pressure. The bulk modulus accordingly relates to the change in volume due to pressure. As I have narrated, important point, not length. So it is change of volumes. So the bulk modulus relates change in pressure and the volume. The negative sign represents the decrease in volume with increase in pressure. Okay, so you can define bulk modulus by the volume stress by volume strain, and you can relate the external pressure with the decrease in volume or change in volume of the solid. Now we are with the basic idea of stresses and strain. We are trying to figure out what can happen in a unit volume inside a body on application of external forces, and of course the body is constrained by some way or the other. Okay, so there are three things that can happen. So what can happen to a unit volume in a material when we apply forces and prescribed constraints to the outside of the body? So it can undergo a change in volume. You can see animated already. It can undergo contraction or expansion. So it is called dilation. Okay. It can undergo a change in shape, as very clearly seen here. So this is the effect of the shear. So the shear actually results in distortion, change in shape. Change in volume, rather, comparative nature, you can see is there is no change in shape, but it retains the shape, is not distorted, but there is some change in volume. The other thing that can happen is everything remains the same. The position and orientation of the body in the spatial coordinate system can change. Okay. I'm animating again. So this is rigid body translation or rotation, but this is more connected to dynamics situation. Okay, if the body is in equilibrium, then the two things that can happen is either change in volume or change in shape. And there may be very complex situation where combination of these things can happen. Okay. So you have an old geometry and you can have a new geometry after deformation. I hope most of the students do some sporting activities and they often twist their leg. Okay, so twisting of leg is a manifestation of the basic mode of deformation, that is due to torsion. Okay, so one common feature, one common fracture mode is a torsion fracture. Okay, so a torque is being applied to a bone, causing a break. Okay, so you can easily understand that if you are playing football or you're running, maybe playing cricket but running, and suddenly you try to move in a different direction, it produces this torsional effect, and you might encounter a fracture due to your demanding complex sort of movement, sudden demanding complex nature of the movement. There may be also other forms of loading which results in torsion and final fracture of the bone. So there are certain data presented in the slide. The shear modulus of bone is 3.5 GPa. The lower leg has a breaking angle of 3 degrees. So these are, important points that are mentioned regarding your bone, which of course, mechanical behavior of bone we will take up separately. But these are sort of data which are based on experiments and clinical feedback together. So it requires about 100 Newton meter of torque to actually break your leg. Sort of a very rough idea. So as you know, that torsion would result in angular deformation, and it is I think there is a small spelling mistake here. Should be shear is related to torque. So this should be corrected. Just a moment. Oh, I didn't realize that this. I'll just correct it here. So the shear stresses, as you all know, the torsion produces shear stresses, and the effect of shear and the and distortion of elements, stress elements, is an effect of the torsional load. So you can, if you revisit torsion, you can easily understand that the different effects you have studied in your basic courses, and of course maybe in your later in your solid mechanics course. So torsion is a very important failure mechanism in case of bone. Now we can apply forces, not stresses. Okay, please be aware that stresses are effects and forces are causing stresses. Okay, so we can apply forces, not stresses, and stresses are developed within the body. These are basic concepts trying to revisit. So if you, this is only shear stresses applied on the body. If only the shear stresses are applied, so if this is the body and within which we can define a stress element, this will be, the shear stresses will be in equilibrium. So if you take a moment about the center point of the stress element, and the center point can be found out by joining with the diagonals. So if you take moment about this, this moment should, this forces causing the moment should balance to give it to be in equilibrium. Okay. Now, if you apply forces on the ends of a uniaxial bar, depending on the orientation of the inclined plane on which you are trying to find out the stresses, the set of stresses, the normal stress and the shear stress occurring within that inclined plane would vary depending on the orientation of the plane. So stresses cannot be defined. Stresses at a point cannot be defined unless you are defining the area on which it is acting. Okay. So these are very elementary things, but very important concepts that you should bear in mind when you are taking up different sort of applications, particularly biological applications. Now, if you pull a body, let us consider this case. If you pull a body in the y direction, will it contract in the x direction? Yes, and that is due to the Poisson's ratio. Although the effect is minimal, but you see there would be some contraction along the x direction. Okay, so the effect of one directional deformation is translated into another normal direction through the Poisson's ratio. So we have these anisotropic crystals on which this effect may be more predominant. Now, as I told you earlier, shear stresses tends to change the shape of the body without changing its volume. So when a body is acted upon by shear stresses, you can see clearly the effect of distortion on the body. Without changing volume, there is change in shape. So we apply shear forces, and shear stresses are developed in the interior of the material, very clearly exhibited here. The stress components, I hope everybody is aware of the stress components in 2D and 3D. So the stress tensors actually take care of the definition of the plane as well as the direction. So as I told you, stresses cannot be defined without the concept or the orientation of the plane. So if you want to define precisely stress, it is the tensor that is more, the tensorial concept is more applicable here because we need to define the plane as well as the direction. Okay, so this is a typical example. You all are aware of it. This is the convention by it follows. So we have the sigma xx or sigma xy. Each notation has its implication. Okay, the first index refers to the plane and the second to the direction. So if we are considering, we are moving into more complex situation, 3D stress analysis. So let us consider a body in the presence of external forces and prescribed constraints, bringing about stresses within a three-dimensional body. So typically, three-dimensional equilibrium we are considering. So you can see the stress components on each face. So each face has the three components here, and it is, if you just go through these basic things, you would be recapitulating all the basic concepts that you have already studied in the earlier classes. Note the directions of the stresses shown are arbitrary. The stresses in general could be compression, tension, and shear could be opposite in sign. So we have just for the pictorial representation, it is shown just for your idea, but the actual directions of the forces are arbitrary, or the stresses are arbitrary. Oops. So in 2D we can write it in this fashion. It's taking the fashion of an array format, as you can understand. So we have the diagonal elements here. Later on, you will realize in 3D cases, finally arrange it in a diagonal fashion. The normal stresses along the diagonal and the shear stresses are filling up the other elements in the array. Now, let us finally come to the hydrostatic and deviatory components of stresses. So the hydrostatic component of stresses, as we had discussed earlier, causes change in volume. So hydrostatic components can cause elastic volume changes and not plastic deformation. So it is causing a change in volume delta V. So that is the reason it is called hydrostatic. It's pressurized from all sides equal, like hydrostatic pressure, fluid pressure, hydrostatic fluid pressure. But deviatoric stresses are actually the stresses that causes change in shape. So if you have if you write down the stress, it has actually the hydrostatic part, which is say the mean sigma m along the diagonal, and a deviatoric part which consists of the shear stresses. So this way, this whole stress, the equation of the stress can be divided into hydrostatic part and deviatoric part in the general form. So this is represented in this manner more pictorially. We come to the last slide. Some examples of loading and deformation of bone structure. So this you will encounter a little bit later, but as you can see, you can have tensile stresses being generated within a bone. You can have shear stresses generated within the bone. A combination of both. Then you can have compressive stresses, you can have bending, you can have different, torsion. So stresses can actually, within a bone sample, within a body, a bone sample is wherever it may be, can be subjected to a complete, a very complex situation which accounts for a combined effect of different kinds of loading. Tension, compression, bending, shear, everything together. So here you can see that this is A is normal stress, B is stress with shear. So normal stress, shear stress, and the deformation of the material is represented in C. So normal distension, C, and in which the extent D, distension with shear, is the angle through which it is changing. Examples of loading and deformation of bone, which can result in different sort of fractures. So different state of stress, as you can see, compression, the stress element here within the body, so typically a femur, is very nicely exhibited. So this is compression, this is tension, this is shear. You can see the change in volume, the change in shape, rather. This is also change in shape, this is torsion, and then bending. Okay, everything together. Change in volume, change in shape, so all together. So this is very clearly exhibited in case of typically a femur bone. Thank you for listening. We come to the end of the lecture. I don't think we have much time to wait a minute, to discuss, but because it's already 10 o'clock, let me just yeah, can you see me? Yeah.
Hi.
Yeah. So we have come to the end of the lecture, so I will upload this. Just a moment. Hello, I'm in a class. Yeah, who are you calling? I'll talk to you later. I'm পরে কথা বলছি, আমি ক্লাসে আছি. Yes. Yeah. You can look into the slides and we can discuss about the different questions tomorrow, because we have a longer class. It's already 10 o'clock. Is that okay? I'll stop recording actually.